Hi, this presentation is about the concept of map and coordinate system. All geographic information system are the computer representation of the real world. So the real world features forms the data for this GIS system. In cartographic models, globes and maps are the primary tools used for the representation of this spatial data. Cartography is basically a science and art of making maps and charts, and the GIS uses maps as input and output of the geographic data. So in this video, we are trying to understand the map elements, and the topo sheets that we have it from Survey of India, and the coordinate system that we are going to discuss. What is a map? A map is the representation of the Earth's surface features or the pattern in the Earth's surface, which is drawn as a whole or a part of it on the plane surface with conventional signs and symbols, and it has to be drawn to a particular scale, and it is to be drawn to a particular projection so that every point on the map corresponding to the actual position of the Earth. Maps are abstract representation of the physical features of a portion of the Earth's surface graphically displayed on a planar surface. Map making dates back to Stone Age and appears to predate written language by several millennia. Map portrays three kinds of information for us: the location and the extent of the feature, the attributes of the feature, which is the characteristics of the feature, and the relationship of the feature to other features, which is called as the topology. How maps convey location and extent. If the map is drawn to proper scale and projection, we can determine the extents of some geographic features. For example, the extent of any of the place in a particular location can be obtained from the linear features, the perimeters, and the area of the features. However, it is very difficult and time consuming to acquire this information by measuring it on in a printed map, and an electronic digital map is required to acquire such information instantly. And how maps convey characteristics of the features. All the characteristics of the features, which is a descriptive information, is given in the attribute table, and the geographic information is given in the form of symbols and labels. For example, roads are drawn with varied line widths, patterns, and colors to represent different road classes in the form of highways, village roads, etc. And streams and water bodies are typically drawn in blue color to indicate that it is a water. And special symbols denote special features such as railways, airports, etc. Thus, the symbols and labels are going to convey the characteristics of each features. And how maps convey special relationship or the spatial relationship is which geographic feature is going to connect the other features, which geographic features are adjacent to another features, which is called as contagious features, which geographic features are contained within an area, and which geographic features intersect each other. So all these informations are implicit when we try to draw a spatial map, and thus we can able to understand the spatial relationship from the maps. Basically, there are some map elements which are very essential in understanding the maps. The first one is the orientation of the map. Always the north should be up, or north should be facing up, which is the orientation of the map. And then scale is the next very important feature or the map element. Earth feature cannot be represented by its actual size, hence we are trying to go for a scale. This has to be in a reduced scale so that every feature on the Earth can be reduced to some scale and it can be drawn on a map. For example, what we are trying to define as a scale is the ratio of the distance on the map to the corresponding distance on the ground is what we call it as the scale. So the example is here. So the distance on the map is 2 centimeter and the distance on the ground is 1 kilometer. What could be the scale? To determine this, we try to take that distance on the map as 2 centimeter, divide that by the distance on the ground, which is 1 kilometer, and you have to convert that into same units so that you get the ratio as 1 is to 50,000. So the scale of that particular map is 1 is to 50,000, which means that the distance between any two features on the ground in reality is 50,000 times reduced in your map. So some example or the details is given here. So we have 1 is to 10,000 scale and 1 is to 50,000 scale map. Which one is going to be a larger map? So a map scale which is 1 is to 10,000 is a large scale map than 1 is to 50,000 map. In a 1 is to 10,000 scale map, which is a large scale map, is represented by a large area of the map, and this is going to give us more detailed information than a small scale map. Large scale maps are typically used to show site plans, local areas, neighborhoods, towns, and cities. Whereas a small scale map is the one in which a given part of the earth is represented by a small area on the map. Small scale maps generally show less detail than a large scale map, and every map will have the scale representation in terms of either it can be a verbal scale, like 1 centimeter represents 250 meters on the map, and 1 is to 25,000 is a ratio scale, and the third one is the graphical scale. Depending on the way in which we want to convey the information to the user, we can select what would be the appropriate scale for our map. And the next element is the accuracy of the map. Accuracy is basically defined as the closeness of measurement or estimates by computation to the true values. Accuracy is generally represented by standard deviation of errors, which is the difference between the measured and the true values. This accuracy generally does not depend on map's scale. Instead, it depends on the accuracy of the original data that is used to compile the map. How accurately this source data has been transferred into the digital map, and the resolution at which the map is printed or displayed. To add more details, the accuracy of the map we create with GIS software depends primarily on the quality of the coordinate data in our spatial database. So to create the spatial data, existing maps might have been digitized or scanned, and the other original data such as survey reports, remote sensing imageries, and data from third parties would have been used. Our final map will therefore reflect the accuracy of these original sources. Maps can be classified as cadastral maps, topographical maps, and thematic maps. Cadastral maps. The word cadastral is derived from the French word cadastre, meaning register of territorial properties. Cadastral map is a map that will show the boundaries and the ownership of the land, whereas topographical maps are called as contour maps or topo maps or topo sheets. Those are the maps that show topography or land contours by means of contour lines. These maps usually shows the contours and also other significant features such as streams, water bodies, forest covers, built up areas, road networks, railway networks, and other features and points of interest. Whereas thematic maps, which is also called as a statistical or special purpose map, which displays the spatial pattern of a theme or series of attributes, in contrast to a general reference maps that show a geographic features, thematic maps emphasize spatial variation of one particular geographic distributions. For example, geological map is one of the thematic map which will show the rock features as the theme. Political map is another thematic map which shows boundaries between different states. A vegetation map is another example for a thematic map that can be used to show the variety of vegetation. So in a broad classification, maps can be of three types like cadastral, topographical, and thematic maps. If you look at the topographical maps prepared by Survey of India, this is going to give us two informations: the physical features, the topography, the drainage, vegetation, as well as the cultural features or the man-made features, which is the road networks, railway network, settlements, etc. The very purpose of preparing this topographical map is to present a sketched picture of the Earth's surface as it is existed during the survey. And Survey of India, which was formed in the year 1767, has divided the entire country into grids of size 4 degrees by 4 degrees, which is called as million sheets. Every 4 degree by 4 degree is going to form one grid, and that is called as a million sheets. And we have index from 39 to 88, 50 index sheets that is available for India. The Survey of India topographical maps has nomenclature, the dimensions and scale is represented in this slide. If you look at the first slide, first picture, this picture is going to give us an information about the million sheet. So the entire country is divided into 4 degree by 4 degree grids, and it is named as numerical values from 1 to 100. And if you take one particular grid, each grid is further divided into a quarter sheet that is called as 1 degree by 1 degree sheet, which is a quarter sheet, and the scale for this is 1 is to 2,50,000, whereas for 4 degree by 4 degree sheet it is 1 is to 10 lakh scale. And this quarter sheet is further divided into 16 grids named from A to P. Each one is having a 1 degree by 1 degree size. And further, this 1 degree by 1 degree grid is divided into another 16 quadrants, which is of 15 minutes by 15 minutes, which is called as a quadrant sheet. And it is also have 16 grids, and the scale of this each grid is 1 is to 50,000 scale. And this quadrant sheet can also be further divided into 4 quadrants, naming this is the north eastern part, and this is the northwestern part, southwest and southeastern part, and that nomenclature is given in this table. Okay, now that we have understood what is a map, what are all the map elements, that is very important, and the classification of maps and the topographical map developed by Survey of India. The next one that we try to understand is the coordinate system. It is very similar to that used to identify locations on a graph or a grid. Example, assigning latitude and longitude to a geographical location is a coordinate system. Basically, there are two types of coordinate systems on a very broad classification. One is the rectangular coordinate system, which uses the distance measurement from origin to describe one's position. The example for a rectangular coordinate system is a Cartesian coordinate system, which uses distance measurement, whereas the next type of coordinate system is the curvilinear coordinate system, in which it uses the angular measurement from origin to describe one's position. The example for a curvilinear coordinate system is a geographical coordinate system that uses latitude and longitude as its measurement. So in the rectangular coordinate system, which is the Cartesian coordinate system, every point in the plane is represented by two numbers, that is called as the x coordinate and y coordinate of the point. And this Cartesian coordinate system can also be used in space, that is in 3 coordinate system or in higher dimensions. The point of intersection of x and y coordinate is the origin. So this point is the origin, and it has 4 quadrants: quadrant 1, quadrant 2, quadrant 3, quadrant 4, and this is named in counterclockwise direction. If you take any point in quadrant 1, both the values are positive. In x value and y value is positive. In the second quadrant, x value is negative and y value is positive. In the third quadrant, both the values are negative, and in the fourth quadrant, x is positive and y is negative. The geographical coordinate system uses a 3-dimensional spherical surface to define the locations of the Earth. If you look at this picture, the equator, which is considered as the 0 latitude, and you have a Tropic of Cancer at 23.5 degrees north and Tropic of Capricorn at 25.5 degrees south. And you also have other latitudes in the northern and the southern hemispheres. If you take any position on the earth with reference to the latitude, it is the angular measurement that is made from the center of the earth to that particular location. For instance, in this picture, it is given the 23.5 degrees north, which is marked from the center of the earth. That is the angular measurement 23.5 degrees. Very similar to that, every other measurements are made from the center of the earth. So this is 66.5 degrees north, 90 degrees north, and then 90 degrees south. The prime meridian, which runs from north to south pole, all the references are made from this prime meridian. Those are called as longitudes, which is east of the prime meridian, and this is 60-degree east of the prime meridian, the longitude, and this is the 90-degree east of the prime meridian. Similar to that, you have a 30-degree west, 60-degree west, and 90-degree west of the prime meridian, and it is again made from the center of the earth. 30 degrees east, 90 degrees east, 60 degrees east, 30 west, 60 west, and 90 degrees west. And east is the direction in which the earth rotates. The latitude and longitude together enable the fixing of the position of the earth's surface. So the horizontal lines or the east-west lines or the lines of latitudes, which is called as parallels, and the vertical lines, which is the meridians or lines of longitudes or north-south lines. These lines encompass the globe and form a graticular network or a gridded network. The origin of the graticule, that is 0, 0, is defined by where the equator and the prime meridian intersect. The globe is then divided into 4 quadrants. The north and south are above the equator. The north and south are above the equator, and the west and east are to the left and right of the prime meridian. Latitude and longitude values are traditionally measured either in decimal degrees or in degrees, minutes, and seconds. So an example for a geographic coordinate system. So a reference system using a latitude and longitude to define the location of points on the surface of the sphere or spheroid. So these two values are same, but the way it is represented is 1 in decimal degrees, that is 92.5, and then degrees, minutes, and seconds, which is given as 92 degrees, 30 minutes, and 0 seconds in the west direction. The shape and size of the geographic coordinate system surface is defined by a sphere or spheroid. However, the surface of the Earth cannot be expressed by any regular geometrical shape. It is Earth-shaped. That is, the Earth as it is with all its undulations, including the mountains and depressions. The Earth is best represented by a spheroid. Although the Earth is best represented by a spheroid, the Earth is sometimes treated as a sphere to make mathematical calculations easier. The assumption that the Earth is sphere is possible for small scale maps, that is 1 is to 50 lakh thousand. At this scale, the difference between a sphere and a spheroid is not detectable on a map. However, to maintain accuracy for large scale maps, that is 1 is to 10 lakh or larger, a spheroid is necessary to represent the shape of the Earth. So between those scales, choosing to use a sphere or spheroid depends on the purpose of the map and the accuracy of the data. A sphere is based on a circle, whereas a spheroid, or also called as an ellipsoid, is based on an ellipse. The shape of the ellipse is defined by two radius. The longer radius, which is called as the semi-major axis, and the shorter radius, which is called as the semi-minor axis. Rotating the ellipse around the semi-minor axis creates a spheroid. A spheroid is also known as a ellipsoid. A spheroid is defined by either the semi-major axis or minor axis, or by semi-major axis and the flattening. The flattening is the difference in length between the two axes. The Earth is roughly an oblated ellipsoid. Because of gravitational and surface feature variations, the Earth is neither a perfect sphere nor a perfect spheroid. The Earth has been surveyed many times to understand the surface features and their peculiar irregularities. The surveys have resulted in many spheroids that represent the Earth. Generally, a spheroid is chosen to fit one country or a particular area. A spheroid that fits one region is not necessarily the same one that fits another region. So, this slide, you could see three circles have been drawn. The red one is the geoid surface, and the dotted lines in green is the ellipsoidal representation, and the brown one is the earth surface. This one is the earth surface. There are many spheroid references exist, each of which is a local geoid approximation. A geoid, in simple words, is the hypothetical surface of the earth that coincides with sea level everywhere. It is nearly ellipsoidal but a complex surface. So the geoid is almost the same as that of the mean sea level. That is, it may be described as surface coinciding mean sea level in the oceans and lying under the land at the level to which the sea would have reached if admitted by small frictionless channels. So the geoid on an average coincides with the mean sea level in open oceans. The mean sea level or geoid is the datum for measurements of heights above it. The geoid may depart from the spheroid by varying amounts as much as 200 to 250 or even more. So the geoid unfortunately has disagreeable mathematical properties. It is a complicated surface with discontinuities of curvature, hence not suitable as a surface on which to perform mathematical computations. Therefore, spheroid is the only option for mathematical calculations. So if you assume the shape of the earth as a spheroid and the projection of the spheroid becomes an ellipse, now we need to look at the semi-major and minor axis distances. In 1866, the mapping of the United States was based on the spheroid measurement by Sir Alexander Rose Clark, and he has done basis of the data collected from Europe, Russia, India, South Africa and Peru, and the estimation of the spheroid allows calculation of the elevation of every point on the earth including the sea level. So in 1983 a new datum was adopted based on the measurements taken in 1980 and internationally accepted as the geodetic reference system, which is called as GRS-80. In 1984, the United States military refined the values of GRS-80 and made World Geodetic System, that is WGS-84 or WGS-1984. Everest spheroid is the reference surface for India and adjacent countries. It was named after Sir George Everest, who was the Surveyor General of India from 1830 to 1843. He was responsible for meridian arc measurements to estimate size of the spheroid. It was originally defined in feet in 1830 and later the values in feet have been converted into meters. These are all the most common approximations when the earth is assumed as a spheroid. The first one is the Everest 1830, which is appropriate for India, where the projection of the spheroid becomes an ellipse and the ellipse has a semi-major axis distance of 63,77,276 meters, whereas semi-minor axis is 63,56,075 meters is for Everest 1830 projections. Whereas Clark 1886, which is for North America, which is for United States Geological Survey, they have identified the semi-major axis has a different value from that of the Everest 1830, and we have the World Geodetic System, which is the current global choice, which has a different value of semi-major and semi-minor axis distances. The next very important concept that we try to understand here is the datum. A datum is a reference from which the measurements are made. In surveying and geodesy, a datum is a reference point on the Earth's surface against which position measurements are made and an associated model of the shape of the Earth for computing positions. So this is called geodetic datum. So it has two dimensions. One is the horizontal datum, which is describing a point on the Earth's surface that is using the latitude and longitude. Vertical datums are used to measure elevations or underwater depths. So a spheroid approximates the shape of the Earth, whereas a datum defines the position of the spheroid relative to the center of the Earth. So in the previous discussions, we tried to assume the shape of the Earth. The shape of the Earth can be sphere or spheroid, and the projection of the spheroid becomes an ellipse, and the spheroid approximations given by many scientists like Everest, Clark, that we try to understand what is the semi-major and minor axis distance. So a spheroid approximates the shape of the Earth. Now this Earth, where we have to keep this in a referencing system, in a frame. So a datum defines the position of this spheroid relative to the center of the Earth. So the origin and the orientation of the latitude and longitude lines are determined by this datum. What is the reference? That reference is what we try to understand as the datum. So hundreds of datums are customized for different parts of the world. So an Earth-centered or geocentric datum uses the Earth-centric mass as the origin of the spheroid. That means the reference from which the measurements are made is at the center of the Earth. So now that is called as the datum. A local datum, which is aligning the spheroid to closely fit to the Earth's surface in a particular area. So Earth-centered is the center of the Earth is taken as the datum, whereas a local datum is the spheroid is closely fit to a particular point. It can be a local area. So a point on the surface of the spheroid matched to a particular position on the surface of the Earth called the origin of the Earth. So the coordinates of the origin is fixed and all other points are calculated from that locations. So spheroid's local datum is not at the center of the Earth. So now we have two datums. One is called as the global datum, other one is called as the local datum. Global datum takes the center of the Earth as the reference. Local datum takes a particular position of a surface of the Earth as its reference. India has the local datum. The location of the local datum is Kalyanpur in Madhya Pradesh, which is the local datum for India. So the initial origin point is Kalyanpur, the latitude and longitude is given there, and the geodinal undulation at that particular point, the geodinal undulation is 0. So any measurements that we want to take it for Indian conditions, if you want to go for a local datum, then Kalyanpur is the origin point, which means the coordinate at that point is 0, 0. From that location, all other measurements are made. So these are some of the examples of the datum. So North American datum, which is called as NAD27. So when we say NAD27, it includes so many assumptions. The assumption is the Earth becomes a spheroid, the projection of the spheroid becomes an ellipse, which has a semi-major and minor axis distances, and the semi-major and minor axis distances is taken from this Clark 1866 spheroid values, and it also has a local datum, that is Kansas, which is located in Medias Ranch, and it is all based on the ground survey information in 1800s. Similarly, we have a North American datum 1983, which also has a assumption that it is a spheroid, but it takes a geodetic reference system, and the ellipsoid is a model, and it is also based on ground data and satellite information. And WJS 84, which is the most recently developed datum, which is the framework for measurement worldwide, and Earth is the centric location from which all the measurements have been made, and this is the datum that is being used in all the GPS satellites. So in summary, this presentation gives you an idea about the maps. Maps are the real world representations. So we try to prepare a map. When we try to prepare a map, we must pay attention in the scale in which we want to prepare the map, and the symbols to represent the Earth features, what kind of a coordinate system that we want to use and that will be suitable for your study, and the assumptions involved in defining the shape of the Earth, its projected shape, and the datum that should be used for your study. This is the end of the presentation. Thank you.